You know that little lock icon you see in your browser? Ever really stop to think about what it's doing? Well, today, we're going to crack the code on TLS. This is the unsung hero, the protocol that's protecting pretty much everything you do online. We're talking banking, browsing, you name it. It's basically the digital lock on your entire online life. Okay, so it all kicks off with a problem that, honestly, seems impossible, right? Think about it. How can you and a server, two total strangers on the public internet, come up with a shared secret key when anyone, and I mean anyone, could be listening in? That's the huge puzzle we're going to solve. To really get why the solution is so brilliant, we first have to meet the bad guys. Let's break down the three big threats that TLS is specifically designed to shut down. First up, we've got confidentiality. This is all about secrecy, pure and simple. It makes sure that when you send your password or credit card info, it just looks like a bunch of random garbage to anyone trying to snoop on the line. No password sniffing here. Next, we need integrity. This is about making sure what you send is exactly what gets received. It stops an attacker from, say, changing a bank transfer from $100 to $10,000 while it's on its way. And finally, authentication. Now, this one is a huge deal. You could even argue it's the most important. How do you know for sure that you're talking to the real website for your bank and not some super convincing fake site designed to snatch your login details? So, to beat these three threats, TLS kicks off a really clever, multi-step process we call the handshake. You can think of it like a perfectly planned heist to create a secret key, and it all happens right out in the open. It all starts with a simple hello. Your browser basically says, "Hey there, here's all the cool crypto stuff I can do." The server looks at that list, picks the strongest option they both know, and then says, "Awesome, let's use that. Oh, and by the way, here's my ID card to prove I'm legit." So, what is this ID card? It's called a certificate, and you can just think of it as a digital passport for a website. It's a formal statement signed by a trusted organization that says, yep, this public key really does belong to this specific website. And inside that certificate, there are a few really important parts. You've got the actual website name, the server's public key, which is crucial for the encryption, and then the issuer. That's the trusted third party, called a certificate authority, or CA. And finally, you have the CA's digital signature, which is the stamp of approval that makes this whole thing trustworthy. But wait, how do we trust that CA? Well, your computer and your browser come with a list of root CAs that are already trusted right out of the box. So the logic goes like this. Your device trusts the root CA vouches for the website certificate, and because of that chain of trust, you can trust the website. All right, now for the really cool part, the magic trick. How do they actually create that shared secret? Well, the modern way uses something called ECDHE, and it is just brilliant. See, instead of one person whispering a secret to the other, it's more like they both do some clever math and bam, they independently arrive at the exact same secret key. It's wild. But the biggest win here is something called forward secrecy. What this means is that even if a hacker steals the server's main key, like years down the road, all your old conversations are still totally safe. That's a game changer. Now, that initial secret they create, the pre-master secret, isn't actually what they use to encrypt your data. Think of it like a seed. They take that seed, mix it with some random numbers they also shared, and from that, they derive a whole new set of keys that are used only for this one single session. And for the grand finale of the handshake, both sides send a finished message. This is basically a cryptographic fingerprint of the entire conversation they just had. If a man-in-the-middle attacker changed anything at all, even one tiny bit, those fingerprints won't match, and the connection is immediately terminated. It's the ultimate integrity check. Okay, the handshake is done. The secret keys are ready. Now we get the payoff. We've built our secure tunnel, and it's finally time to start sending some actual data through it. So how do we protect that data? Modern TLS uses a beautiful concept called authenticated encryption, or AEAD. It's the super efficient 2-for-1 deal. With just one operation, it scrambles your data to keep it secret, and it creates a special tag to make sure nobody has messed with it. Here's how to picture it. For every little piece of data you send, it gets bundled with an authentication tag. That tag is like a tamper-proof seal on a package. If an attacker changes even a single bit of your data, that seal is broken, the tag won't check out, and the receiving end just throws it away. So the system seems pretty much bulletproof, right? We've covered confidentiality, integrity, and authentication, but this entire fortress of security is built on one single, very important assumption, and that's its weakest link. What happens if the very foundation of trust gets corrupted? What if one of those root certificate authorities, the ones your computer trusts without question, is actually a fake, planted there by an attacker? Here's how that nightmare scenario plays out. First, some malware infects your computer and sneakily installs a fake root CA. Next, when you go to your bank's website, an attacker intercepts you and shows you a fake certificate, but it's signed by their fake CA. Your browser looks at it, sees that it's signed by a CA in its trusted list, and shows you the little green lock. You think you're safe, but the attacker is now in the middle, reading everything. And here's the really mind-bending part. In this scenario, the TLS protocol itself isn't broken, not at all. It's actually working exactly as it's supposed to. It's correctly checking a certificate against a trusted authority. The problem is that the trust model itself, the very list of who to trust on your own machine, has been poisoned. So, let's wrap this all up. TLS is an amazing piece of engineering that gives us our 3 big security guarantees. The handshake creates those secure keys with that incredible forward secrecy. Then the protocol uses super fast modern crypto to protect the actual data. But the whole thing, all of it, hinges on the integrity of those trusted root CAs on our devices. And that leaves us with one last really big question. TLS gives us the cryptographic tools, the locks and the keys, to be secure. But if all that security is built on a foundation of trusting these guardians, then who exactly is guarding the guardians?